Hello, everyone, and welcome to this Surface Ventures workshop. Please say hi in the chat box and tell us where you're joining from today. My name is Dr. Sam McMaster. I'm the content manager here at Surface Ventures. We are a non-for-profit organization, and our mission is to provide world-class surface and material science education for academia and industry. Today, it's my pleasure to introduce Dr. Florian Papa of the Leibniz Institute, or Leibniz University, sorry, at Hanover. Dr. Florian Papa is a postdoctoral researcher and project manager at the Institute of Machine Design and Tribology at the Leibniz University, specializing in materials engineering, manufacturing engineering, and tribology with expertise in tribal physics and tribal chemistry. Dr. Papa has a strong background in thin film technology, laser cladding, rapid prototyping, and laser foaming. Currently, Dr. Papa is focused on the influence of tribal films and micro textures on friction and wear, sensors, sensor integration in bearings, and the use of graphene as a dry lubricant or grease additive, while also managing several DFG-funded projects and teaching bio and microtribology over the past 5 years. In addition, we'll be hearing from Dr. Jaroslav Lukasz and Dr. Ude D. Hangen of Bruker. Dr. Lukasz is an application scientist for Bruker Nanosurfaces and Metrology, specializing in nanoindentation and products and thin film ellipsometry. He's an expert in the mechanical properties of biomaterials and mineralized tissues, such as bones and teeth. Dr. Lukasz leverages his extensive knowledge to advance the understanding and application of nanotechnology in these critical areas. And Dr. Hangen is an application scientist for Bruker Nanosurfaces and Metrology and serves as the applications manager for nanoindentation products. He specializes in the plasticity of metals and ceramics, focusing on testing these properties at the nanoscale. Uda has worked on the standardization of hardness testing and is the project lead for advancing the understanding of test methodologies, defining new approaches to measure nanoscale material properties beyond hardness and reduced modulus. Many thanks to today's partner, Bruker. We will have a short presentation for Dr. Lukasz after Dr. Papa's presentation and a video demonstration of the Hysitron TI990 Triboindenter from Dr. Hangen later in the event. We'll also be releasing poll questions and handouts from Bruker. As we go along, please type your questions into the chat and they will be marked for the Q&A sessions. And we're planning to go for around 60 minutes today in total. We will be sharing a link for your attendance certificates later in the event. So without further ado, let's welcome Dr. Papa to the stage. Then we'll bring his presentation up.
Yes, thank you for your nice introduction.
You're welcome. There are your slides, and I'll let you get started. Thanks.
So, right, I'm happy to present about the nanomechanical research on tribo-layers that has been conducted for the last years at the Institute of Machine Design and Tribology in Hanover. Currently, we also have a very big project running. It's a DFG-funded project Awareness, where we investigate the tribal film formation on bearing surfaces and discs running in a twin disc setup, where we want to gain knowledge in the wear and the tribal film formation, so the positive and negative wear. This project is running together with Professor Popov from Berlin, who works on the material removal based on the Rabinowitz criterion, and Professor Pastewka in Freiburg, who works on the molecular dynamics on the film formation, where we are all connected together, the EMKT more on the micro scale and mesoscale, to apply wear calculations according to Achar and Fleischer. As I said, Professor Popov is working on the simulation parts on meso and micro scale, and on the nanoscale directly Professor Pastewka. And in this field, to gain knowledge on the tribofilms is mandatory, and the nanoindentation, of course, is a very important tool for us. The motivation why we started this project is based on the reduction of friction and to avoid wear on bearings in gears. Here you can see a Mercedes-Benz 7-speed automatic transmission, which is quite complex. We see a lot of radial and axial bearings, allowing us to transfer the power from the engine. And we have the wish that such very resource taking machine elements can last for a long time, more than 150,000 kilometers for many years under cold conditions, hot conditions. So we have to optimize the operating conditions in these machine elements, reduce wear, achieve the low frictional losses, and to do this, additives in the oil are mandatory. They are crucial to achieve these aims, but we still have to gain insight into the tribofilm formation. It's not completely understood how it works. There are many working groups working on, and we also have to understand the influence of temperature, load in this complex play with the additives. To qualify the gear oils, there's a test trick as shown on the right at our institute. It's a standard test for gear oils, the FEA test. On the left, we can see the bearings. It's axial bearings in this red circle, which are investigated under grease or oil lubricated conditions. High load is applied with disc springs and axial load, and these bearings run under harsh conditions, under high load, under increased rotational speeds. And for the first 500 RPM is for 1 day, like a run-in, and after that for 176 hours under 750 RPM. And the temperature, we investigated the bearings up to 120 degrees Celsius. And to qualify the oils with additive packages, these bearings have to stand this 200-hour test. So this investigations give us information on the boundary layer generation. We can investigate the frictional torque during the test and afterwards investigate the tribofilms directly in this FEA test trick. And of course, we can also work on tribometer level to investigate the film formation on tribometers, but also to investigate the tribofilm by tribometers after the test. And what we had been working on in Hanover, I would say the EMKT started with the Institute of Microtechnology nearly 20 years ago to apply nano-indentation techniques. They started with the triboscope to achieve the nano hardness and Young's modulus of these boundary films. And we can also gain insight into the elastic and plastic deformation and on local friction coefficients by performing nano scratch tests. By using tribometers, the frictional properties of the surfaces can be achieved as well. And a lot of work has been done in this past 2 decades together with the colleagues in Münster, the group from Professor Allinghaus, with the time-of-flight secondary ion mass spectrometry to analyze the adsorbate and boundary layers, the distribution of elements and molecular compounds, and also the depth distribution of these elements by sputtering away some amount of the surface and then investigate the distribution of elements again. But back to the basics, we have to understand at first that we have very high load in the bearings. On the left, we can see a ball running on the raceway. we have a normal load and a resulting contact ellipse, as we have an Hessian contact stress. You can see on the right the lubricant inlet in the zone, and we have an elastic deformation of the ball and the raceway itself, and a high pressure in this zone. Additional also an increase in temperature. And under these conditions, the lubricant forms tribofilms, which are glassy-like. So here's an example for such a tribofilm, and a typical anti-wear additive, it's called zinc dialkyl dithiophosphate with zinc and phosphor, sulfur in this complex additive, and it's used since the 1950s as additive for gears to avoid wear. And we achieve classy iron zinc polyphosphate tribofilm with the thickness of 100 to 200 nanometers on the surface of the bearing, with a fine surface roughness as shown here. This is a scanning probe microscopic image done at an axial bearing washer. And we also want to gain knowledge on the influence of the tribofilm on damping and elastic properties for the bearing. What's quite important with the EV vehicles and also for the wind turbines is that we want to gain knowledge in the electric conductivity of such tribofilms and how to enhance these tribofilms, the local friction properties where we can work on, and of course the wear rate to put it on our simulation models. What we have to know also about the tribofilm is the growth rate. We have here the form of the I-ring model, this equation, where we have in this exponent the activation energy, the delta U activation, which is like a barrier for the formation of the tribofilm. And this barrier is reduced by the shear stresses, this tau, which is acting on the volume, and also the temperature reduce this barrier. That means by increased shear stresses on the surface, it's like a catalytic reaction, we enable the film formation, and by the kinetic, it forms the tribofilm according to the temperature increase, as shown in the diagram on the right. And the third term, the P delta omega activation, this shows us the compressive stress, which also influence the activation energy, but this term is still under discussion by groups like Karpik and Spikes. Back to our bearing washer. Here on the left is a fresh bearing washer that is used in our test rig, in the FEA test rig. And after the test, we can see a very nice tribofilm on the surface in the middle of this slide. The color is from slightly bluish. Some parts are slightly red. And the tribofilm formation depends on the additive package that we use. It can be ZDP. We can also have some calcium sulfonate and other additives in to improve the anti-wear properties, but also extreme pressure against oxidation of the lubricant. And of course, the temperature influences tribofilm formation and the local load and kinematics. For this kind of axial bearing washers, we have to regard the slip-to-roll ratio independence of the position of the roller to the raceway. And what we can see here in this image on the bottom, we have the adsorbate layers, which we can investigate also with our time-of-flight secondary ion mass spectrometry, and then the chemical reaction film, the reaction layer, which is very important to avoid wear. Here is a closer view on the contact conditions for the bearing. On the left is again the surface with this slightly blue color or slightly purple. And in the middle we can see the contact ellipse and the product of the Hertzian stress and the sliding speed, which show us also the slip-to-roll ratio for this kind of bearings. And what is quite interesting, on the right, we did some ultrasonic scans of the bearings. We put it to an ultrasonic microscope, which allows us to achieve cracks that can occur subsurface. That was under certain test conditions that we achieved these cracks on this kind of bearings in the test rig. And there we also did some cross sections on the rollers where we can see the cracks subsurface, and on the right there's a crack opening of this axial bearing washer. And this is a quite complicated problem for bearings, which we also wanted to gain insight by studying the tribofilm. So doing this, in the first step we did the non-indentation studies. And the benefit of this is that we can indent into the tribofilm under low loads and achieve the elastoplastic properties. And I took with here an old slide we prepared for the triboscope, where I started my work at. I also visited my first time Ude in Ismaning at that time. And we can see here the tip, which is mounted on a pickup electrode, which is placed between two plates, allowing us by electrostatic force to displace the tip into the substrate. And by a change in capacitance, we can measure the displacement itself. So it's very precise to investigate the response of our material to the applied load. And by a so-called X system, the middle system can be also moved along the surface, allowing us to perform a scratch test. On the right, there's a SEM image of a so-called Berkovich tip, which is commonly used for the hardness measurements. So the material response, it's shown here. It can be like more elastic on the left or ideal plastic. In this case, there's just the indent and no elastic response of the material. And typically for our steel substrates and also for the tribofilm, we have this elastoplastic response. That means there's a plastic zone below the indent, but also some elastic properties of the material. For the measurements on our bearing washer, it's shown here. We can see that along the raceway, the hardness is reduced due to the tribofilm. For tribofilm, then we indent very precisely under very low load. It's a hardness below 2 to 4 gigapascal. But here we still have some influence of the substrate itself. But on the high slip zone, where we have high tangential shear stresses, there's a tribofilm thicker, and we achieve the lowest values for our tribofilm. And in the middle, there's the no slip zone, and thus, when we think on the iron model, lower flow rate of the tribofilm, the hardness is slightly increased. And for the elastoplastic material behavior, on the right, there is some exemplary nano indents outside of the contact zone. We see that there is the material behavior less plastic, and in the middle of our bearing washer, slightly on the high slip zone, you can see a very deep indentation and also a large amount of plastic behavior for this tribofilm. To gain more information, we did some nano scratch tests. So the principle is shown here. For this, we used a conospherical diamond cone tip, and we scratched along the surface with increasing normal load, and we can measure the pileup aside and also the plastic and elastic deformation. Doing so, we measured in 3 steps that we can see here. When we go to the upper diagram, we have here the black curve. It's a scan under very low load of 2 micronewton along the scratch surface, but to achieve the profile before scratching, after that, we go to the start to the left and increase the load and perform a scratch test. That's the green curve. And after that, we scan along the surface again and achieve the red line, which shows us the plastic deformation which remains on the surface. Like in this image below, that's the remaining scratch, which is here shown in red. And we can see that the tribofilm formed on the bearing surface features more plastic properties compared to the steel itself in the diagram shown for the steel liner. What is also very worthy, that we can achieve the frictional properties during plowing into the substrate, that's shown on the right. And the black curve is for the tribo-layer. So here we achieve a more or less stable coefficient of friction of approximately 0.25, while for scratching in the steel substrate, we have a coefficient of friction from 0.05 at the start to 0.4 for the plowing into the steel. So this is quite interesting to have that data. And later on, I will have a slide to show that we are proceeding here. We also did some measurements with a pin on ring test rig shown on the left, where we can see that the friction of this tribofilm is quite low with a value of 0.09 to 0.1, while aside it's slightly higher. So we can also achieve the frictional properties of this tribofilm, but with the pin on ring tribometer, not that precise as we would like to do. For the TOF-SIMS measurement, just short, here we have the surface imaging to investigate the lateral distribution of elements and molecules on the surface. This is done that there's a mass spectrometry measurement of the secondary ions which have been desorbed from the sample surface and the spectrometer itself. And we can also do some depth profiling. In this, we sputter away some amount of the surface in the range of a few 10 or 100 nanometers, and then repeat our measurement again. In doing so, we can achieve the distribution of the elements on the surface and also in the depth. And there are some very interesting elements that we can see, like the calcium from the additive, or also the phosphate classes that are formed on the surface. On the right, there's exemplary the calcium signal, and in combination, the diagram with the sulfur and also the calcium phosphate classes formed on the surface. And we can see also that the slip-to-roll ratio has an influence on how this kind of tribofilm is formed. What we can do with all this data is that we can use it for our simulational models. One example is shown here, that we applied to our simulation the surface roughness from the SPM images and also some local friction coefficient. In the simulation for the bearing washers, to know about the crack opening regarding the wide etching cracks, and also to understand how hydrogen can get into the steel regarding this specific surface and voids that can occur in this kind of surface that we also detected for specific samples. And we are still going on with this kind of measurements. Here's an example we generated at Bruker in Karlsruhe, where I took with some PRO oil with ZDP and graphene, and we investigated the friction regarding an increase in temperature from 30 to 100 degrees. And what is very nice, we can see under room temperature in the diagrams for the tic-tac surface profile, we achieve some wear on the surface. And by increasing the temperature, the tribofilm increases as well, as we can see also in our iron model for the growth of the tribofilm. And Uda did some very nice measurements of the hardness on this layers, showing us the hardness on the specific tribofilm itself with values of 3 to 4 gigapascal. And what is quite new, he did an array of nano scratch tests on this kind of tribofilm, shown here on the left, for the sample under 100 degrees of Celsius formed in the tribometer. And we can see that we have here a local coefficient of friction of slightly below 0.1. And we compared that to the measurements done at the micro pin on disk tester, which are also could put in an oven up to 70 degrees or 100 degrees. And we can see that this curves fit quite well to the measurements done with the nano scratch tests. So here we can really see some local coefficient of friction of the ZDP-based tribofilm. And I hope we can proceed with this work in the future too. So to the conclusions, the nano indentation gives us knowledge into the tribofilm, which is mandatory to simulate tribological effects, thus allowing us to improve mechanical and frictional properties for bearings and gears. And further on, we can save resources that machine elements can run longer and use less energy. The tribometer tests allow us to achieve the frictional properties during the tribofilm generation, but also after some FEA test tricks, of course. And the utilization of sliding contact condition give us information on the film formation, like that it depends on the sliding energy and is enhanced by the temperature, that we have here the effect like with the catalytic substance. And we have a high influence of the temperature on the formed tribofilms, and the TOF-SIMS profiles give us some knowledge about that we have some phosphor-based phosphate classes on the surface, and that there's a high influence of the slip-to-roll ratio on the formation of the tribofilms. And what I want to show slightly shortly is that we are also going on to extend our knowledge on the formation of tribofilms or boundary layers in cutting processes. On the left, we can see a ship formation with a cutting tool, which is done together with the IFW Institute in Hanover. And we use also knowledge from nano indentation and TOF-SIMS data on the simulation of this specific contact and gain knowledge how metal working fluids can improve our cutting processes. So here's an example of some investigation of the nano indents on a ship. Here's a ship surface, and below the indentation depth of our nano indents, where we can achieve the nano hardness or the reduced Young's modulus and compared to samples that we produced by dipping heated samples of metal into metal working fluid to gain knowledge how high had been the temperature that the tribofilm was formed in this cutting process. So thank you for your attention, and also thank you to all our partners like the IFUM and the IFW, EMPT in Hanover, and the WWU Münster that had been working with us in the recent years.
Thank you very much. Fascinating talk. Really interesting to see, very in depth into tribofilm formation there. So right now we'll be switching over to Dr. Lukasz's talk. So let me invite him on stage right now. So just a reminder to everyone in the audience, if you have any questions for any of our speakers, please type those into the chat, and we will address those later in the event.
Thank you, Sam.
You're very welcome. Just stay on stage just to check that your slides are showing. Once that's done, we'll proceed. Okay, brilliant. I can see your slides. Take it away.
Okay, so thank you, Sam, for the introduction. Thank you, Florian, for very nice talk on tribofilms. I'll spend some time now on a bit different topic. So again, it's going to be related to nanoindentation and the triboindenter, but I'll be specifically talking about some property mapping, like hardness and modulus, that Florian was also showing in his presentation. And you will see also a bit of a demonstration after my talk. So just briefly remind you what the indentation is and what are the default values and the basic parameters that we can get, because that's also important for some of the consideration that you need to take into account when you start doing some mapping. So the main output from nanoindentation is the hardness and modulus that we actually analyze from the unloading segment of the indentation curve, which is a load and displacement curve. So the most influential parameter here is the contact area. So the contact area is a real-time contact area at the maximum force. So our tip and the geometry of the tip is very well calibrated on a standard material of a fuse quartz. So we do a lot of indents at different depths. And since we know the mechanical properties of this standard, so we know the elastic reduced modulus, so we can calculate what is the contact area needed to get this reduced elastic modulus values. And that's the way how we can construct the so-called tip area function, which is a function of a contact area with the contact depths. So this is the most influential parameter, and basically what that also means is that the reduced modulus is kind of given by the slope of the unloading segment, so how the material is pushing back the tip when you are unloading, and the hardness is simply the maximum force divided by the contact area. So we need to produce some deformation to the material to actually get the hardness properties right. But I'll talk about that later. But the most important thing is that we are penetrating into the material and we are collecting a load and displacement data. And if you look at these indentation curves on the different materials, you might already get the idea what is the material about. So if you look at the crystalline metal, you see the discontinuities that are related to the plastic deformation. So we see some elastic deformation in the beginning, and then this material starts plastically deforming. The other materials have a different shape of the unloading segment, which results in a different value of an elastic modulus. So if we are indenting a homogeneous material, we collect very similar looking indentation curves. But when we are dealing with very heterogeneous materials, like for example here in we are looking at the Damascus steel, so we see a different layers. If we zoom in, we see a different phases in the microstructure, and we can also use our indenter tip to get this topography image over a sample surface, so we can distinguish and visualize these different phases. So traditionally you could go and point into these different phases and get the hardness and modulus with the relation to the local microstructure. And in these days, the nanoindenters allows you to do a mechanical mapping. So the very latest Triboindenter TI990 from Bruker enables to do 12 indents per second. So you are running the indents in the line, so you can you might be able to actually get the contrast on the mechanical properties with respect to the different phases. So how that works, you are focusing on a surface with a microscope, and then you synchronize the motion of a piezo scanner over the sample surface with the sensor that produces the indents and collects the indentation curves. So this is the video from SEM Pico indenter. So we also have the indenters that go to a strain electron microscope or transmission electron microscope. So we see different phases, and then the indents, you run the indents in line. So this can be done in a very fast manner. So with the latest Triboindenter, you can do 12 indents per second. So you can collect these maps and these individual points very quickly. So if you do everything ideal, you might result in a map like this. So this is the map over the Damascus steel. So this map actually is composed by 1 million indents. So you see lamellas, you see different layers. You can actually zoom in and also analyze the different phases that you have. So this is very nice results, and I would like to focus now how or what are the considerations behind the loading protocol that you need to apply to get such a nice result. So the most basic question that I usually get is how close we can get the indents together, and what is basically the resolution of such a map. Right. So I must say, you have to think what is the output and what are you interested in. So if you are interested only in the elastic properties, you have more freedom. If you're interested in the absolute values of the hardness, then it starts to be a little bit different story. So let me just remind. So if you do a very shallow indent in the elastic regime, so the load and unload will actually go along the same line. So you create an elastic zone under the indenter, and if you unload, there is no residual indent, there is no residual deformation. So in this way, you can measure elastic modulus, but in case of a hardness, you have to actually go over the yield strengths of your material. So you have to produce a plastic deformation. Otherwise, the hardness value that you measure is not really reaching the intrinsic property of your material. So you need to produce a plastic deformation zone together with the elastic zone. So elastic zone is always bigger than the plastic zone. So plastic zone is smaller. So so that also means that if you have a different phases around, the plastic zone or the hardness value is actually less affected by or it's more local. Right? So you measure the hardness in a more local way. So that's one thing that you have to keep into consideration, and you have to keep the separation enough to prevent any influence of the neighboring indents, right? So this plastic deformation zone should not be part of the next plastic deformation zone next to the previous indent. So this is something that's so these images are describing something that I just a bit explained. So I would say it actually the deformation zone is a function of tip radius and material itself. So the best way to do it is just you make a test and you see the influence, or you measure the influence, and then you can decide what should be the separation. Otherwise, there are some rule of thumb values that you can apply for different types of materials. So in this case, if you change the distance, the spacing between the indents, you see how the hardness and modulus values are changing with the spacing. So of course, if you deform your surface with your indents, and then you're producing an indent next to each other, the contact area is also deforming, so or is also affected by the by the plastic deformation next to it. So this has an influence on the reduced modulus as well. So you see that there is some kind of a threshold where there is no influence. So you get the plateau. So basically the properties are not changing anymore with the indent spacing. So this would be the ideal spacing for your map. If you have a different phases which you want to map, you also need to keep your deformation zone local to measure just the intrinsic property of a single phase. So you can also do some kind of so if you want test depths, you can also do like a depth profile of mechanical properties. So this is the depth profile of hardness and reduced modulus when you are indenting in between of two different phases. So you see that you get the intrinsic property for very shallow indents first, and then you are measuring the mixture, so the average property of all the phases involved, and at some point the indent is too big, so you're really measuring just the neighboring phases, and you're not actually getting the information for this little phase in between. Right? So you also need to think about the so besides the indent spacing, you also need to think about how deep you need to go to be sensitive, surface sensitive, and sensitive to the specific phase. And then ideally, well, if you're just interested in the elastic modulus, the spacing can be actually very, very small, because there is no plastic deformation left, so there is no deformation of the surface. There's supposed to be no change in the material properties after unloading, so you can actually space the indents very close to each other, so you get like flat line for the reduced modulus over the lateral positions here. So elastic modulus is actually more forgiving, let's say, if you're interested in the elastic modulus only, but the hardness is a very different story, because you have to take into account the plastic deformation zone under the indenter. So let's say the takeaway message from this slide is the indentation spacing and the depths that you want to produce. So the smaller is the indentation depths, the smaller can be the spacing, and the higher is the resolution of your map. But since hardness is depending on the plastic deformation, you also need to take into account the geometry of your probe. So this is also a very influential parameter. So if you have a dull probe, you produce the plastic deformation in the later stage. So you have to push the probe push the tip into the material deeper to produce enough plastic deformation to measure the intrinsic property of hardness, or intrinsic hardness of your phase. So this is like 3 different examples of 3 different tips. So the first tip is quite sharp. It's a very sharp tip. Radius at the end is 35 nanometers. The second one is 80 nanometers. The other one is half a micron. And so as you can see, you start measuring the real hardness values at the very different stage, or from different penetration depths. If you look at these curves, right? So you see the increase in the plastic deformation, basically the stress level in your material. So you're increasing at some point, you are reaching the yield stress. So this is the plateau for your hardness values. So if you want to have, or if you want to reach very high resolution on your hardness map, it's also beneficial to have very sharp probe, because then you can produce small indents, produce the high stresses right from the beginning, and then you can pack the indents close to each other and reach the high resolution in your hardness map. So if you do all this, indent spacing, you think about your indentation depths, and you have nice and sharp probes, then you can do very interesting and nice study on the different materials over even larger scale. So you can really go from like a micro scale to hundreds of micron scale. So as you can also see here in this example, the hardness map on this alloy is actually giving quite a nice contrast, because the hardness is very much related to the different phases that you have, and it's measured very locally. Elastic deformation zone is actually very, very big. So you might actually measure the average properties right from the beginning. So hardness is giving a very nice contrast. Or this method technique can be applied on the composites. So you see the different phases on the hardness or the modulus maps. Or you can also correlate these maps with other microstructural studies like EBSD or a chemical distribution, which are also nicely linked to the hardness values here. After collecting all these data, you also need to analyze them. So we do have a tribo-IQ package. So it's a software that enables you to do the clustering, but I won't go into details due to the time reasons. And there is also a separate webinar that was released in the past from Bruker. But just briefly, if you have all these maps, hardness and modulus maps, that you can also create clusters with some of the machine learning approaches, for example. So in this case, I'm presenting clusters measured at different temperatures. So you can also break the microstructure into different clusters and study those clusters, how the material properties are changing with the temperature for different structural organization or crystallographic orientation. So this is, I would say, quite a popular approach nowadays. And since the measurements is very fast, you can also do it, or you beneficially do it at high temperature, so you don't really consume your tip too fast when you're using this fast indentation approach. So thank you for your attention, and that's all from my side. And we can look forward to see some demonstrations.
Okay, thank you very much, Yaroslav. Right, so now we'll share the video of the TI990 Triboindenter. So just for everyone's information, this is about just over 12 minutes long. So we'll have time for 1 or 2 questions afterwards, and then we'll wrap up pretty quickly after that. So Yaroslav, just once I trigger this video, let's both leave stage. Okay, enjoy the video, everyone.
Hello, this is the new TI990 Triboindenter. It is completely redesigned for the future of nanomechanics. It does have a new control electronics, the Performic 3 controller. It does have a new software that is easier to use and allows for more options to be tested. It has a redesigned enclosure in stage to allow better isolation and to allow more space for even more samples. And it also does have a large door that gives access to the stage for easy placement of a lot of samples or advanced testing options.
Hello everyone, welcome to our lab and the introduction webinar for the latest Hysitron TI990. Here we can see the top of the enclosure and the computer workstation. We can use Dr. Eric Hinstella for a sense of scale of the tool. The enclosure utilizes a large door for ease of access. As you can see, everything has been redesigned from the previous generations of tribo-indenters. That includes new framing, new controllers, and an entirely newly optimized granite bridge. Currently, it is set up in a 2 transducer or dual head mode. On the left, we see a 3D Omni probe, and on the right, we see a Nano DMA4 transducer with piezo scanner. We can use the higher force 3D Omni probe for deep indents and scratches, and then SPM it using the low load transducer setup. Triboscan 12 represents an entirely new era for Bruker's Hysitron line, no longer running in lab windows. Both the GUI and underlying code have seen significant improvements with the data front and center, and the progression through the software panels flows logically from top to bottom and left to right. Let's start with creating a new workspace which saves all the settings like sample boundaries and calibrations. The system calibrations can also be found here. Next, we have the load function panel, which allows us to optimize the test parameters. We also have a few default load functions, as you can see here. Then we have the automation tab where we can create stage method automations and chain longer, more complex automations together. There's also an option for piezo automation from imaging mode, but we'll see more details of the imaging mode in a little bit. So let's come back to the sample exchange mode now, which basically homes the Z stage and brings the sample chuck all the way forward, giving you easy access to change or mount new samples. This is a multi-purpose sample chuck with various mounting options. So we have magnet locations, vacuum rings of various sizes, screw locations for mounting sample mounts, and so on. Here we have our application scientist mounting a high entropy alloy sample onto a platen and bolting it securely to the stage. We use a top-down navcam, which is mounted on the inside of the top enclosure. The microscope optics are good for navigating around a particular sample for locating areas of interest for testing, and the magnification is optimized for looking at the overall stage setup for with multiple samples. We can use this navcam now to define all the samples from one field of view. So once we have the samples mounted in there, we can open this navigational camera tab and you can do a quick and easy way to define where all the samples are sitting. We can take a navigational camera photo. This is this top-down camera that you saw earlier mounted to the top of the chamber. It's going to really help us in giving an overview of what is on the stage, especially if you are running the system remotely. Okay, so now that we've got our new picture here, we can go ahead and define samples. And so here, you just select a new sample and give it a name. This is a polycarbonate sample, and we can define the sample from the navcam optics, and we can go through them and quickly approach all of them so that the software knows where they all sit. Let's make another sample, fuse quartz here, and just create the boundary by double left clicking on the sample corners. One more sample here. It's a high entropy alloy. So now that all the samples are defined, the system can go ahead and automatically quick approach all of them. And you can just pick the tallest sample on the chuck. It's the polycarbonate in this case. And this sets the Z fly height based upon that. This part is going to take a few minutes per sample, but it's going to go through all the samples automatically. We can see here inside the enclosure how the sample stages move for the quick approach of all of these samples that were just defined. Now I can go select the sample that I want to run tests on and right click inside the defined sample boundary. We can navigate through the sample here in X and Y directions to choose the area of interest for measurements. Now let's go into imaging approach where the scan settings can be defined and the sample can move to be under the piezo transducer setup to scan the surface of the sample. There are a number of imaging parameters to optimize the size and speed of your scan. Clicking on this play button is going to start the scan here, and we can visualize the topography as the scan progresses. We are able to start the scan at the top, bottom, or center here, and also change the scan directions. Let's speed up the scan here and save it. Now, this is the area that I've scanned for an XPM test, which is accelerated property mapping. And I've created a load function. This is the displacement control test going down to 30 nanometers and a 10 by 10 grid with 200 nanometer spacing. So it lifts off the surface and reseeks to find the sample surface. Basically uses a trigger force to identify the surface. We're able to run in displacement control and out of contact using those trigger values to help deal with the sample tilt and topography. So this is the real-time plot for that XPM test that we just created. We can speed it up and look at the data quickly. We do almost all of our data analysis using Tribo-IQ, which is an origin-based app. We have a number of apps for various test types. Let's start with the Indentation Explorer here to look at the data. So now I'm going to import test files created in TriboScan directly into TriboIQ and start analyzing the data. Here I'm looking at the load displacement curves from one of the XPM files, and let's re-zero them with an automated algorithm. Now, when we zoom in, we can see how they all have that maximum displacement of 30 nanometers. And we can run analysis on these curves to generate hardness and modulus values for each of the tests. This is what the data looks like, and let's export that into a text file to use with the other XPM app. Here we have that test file, which plots the data as a property map using the XY coordinates. Now we can select hardness maps or modulus maps. Now, here is a single XPM test with a 12 by 12 grid covering about 2.4 micrometer square area. We can use this test and stitch it into a larger area using piezo automation, allowing us to make larger maps. This is a 7 by 7 grid with 2.6 micrometer spacing of that XPM test, covering around 20 by 20 micrometer square area. Now we can import all of that data into our XPM app here and see what the larger maps look like. We can clearly see the different regions here showing variations in the properties as well. We can further analyze this data set by separating it into different regions and finding out the average properties of each clusters. This has been covered in the TriboIQ webinar. We can also look at this data in the form of a histogram to see the distribution. We can divide it into different number of bins depending on the total number of data points. In order to automate the AC force setting, we are going to run an indent that tunes the force amplitude using a displacement set point. This measures the stiffness response and sets the correct amplitudes with a feedback routine. So we'll start by selecting the sample and clicking on this depth tune button here. This is going to be on the polycarbonate sample. A simple linear fitting is used in most cases. This tuning is then applied to the sample to maintain a set point as a function of depth during our continuous measurement of X or a CMX indent. After this depth tuning, let's run a CMX test on the same polycarbonate sample in displacement control. So I'm adjusting a few parameters here and making sure the displacement amplitude is roughly 1 nanometer for the test. Here we start by lifting off of the surface to make sure we are completely out of contact before we start indenting. We are going down to 2 micrometers here to get the depth profile. Now we are using tribo-IQ again here to look at this CMX data. We can see the displacement amplitude here as a function of contact depth. And also storage modulus can also be seen here as a function of depth.
Okay, everyone. I hope you enjoyed that video. That was certainly very, very in-depth and great to see the Triboindenter in action. So now I will release the attendance certificate link for everyone. So you can now go ahead and click on that. And I'd like to welcome all of our speakers back on stage, please. We'll do a couple of questions before we wrap up this event. Welcome to the stage, everyone. Okay, I think our first question is from Himanshu. I hope I'm pronouncing that correctly. And they ask, how reliable are indentation results in the case of nanostructures, hundreds of nanometers, specifically hanging nanostructures, as the tip size is higher? Question mark. I guess they're asking. Sorry.
Yeah, maybe I'm going to answer that question. I think it's related to my presentation and the size effects and things like this. So if I understand correctly the question, so we are indenting with the tip, which is 40 nanometer, 100 nanometer radius at its apex. And if you want to indent something which is smaller than this, so how reliable is this? Well, of course, it a little bit depends on the geometry of these small things as well. So as I explained during my slides, my presentation, you have to produce a plastic deformation. You need to have a flat surface to get the contact area right and get the hardness and elastic modulus right. So there needs to be enough material to have the flat surface and produce a plastic deformation. So that's of course needed. Otherwise, if you have something small in the like embedded in the matrix, for example, and you are indenting into these small features, you're still sensitive to that, but you see the effect of the surrounding matrix as well. So you are measuring a mixture of the properties. So the only way is to really have a smaller chip. So there is a big limit that we can measure, of course, due to the tip size and the tip geometry.
Okay, thank you very much, Miroslav. We have another question from Dino, who asks, has there been changes to nano DMA? That's a specific application.
Yeah, maybe I can answer that. So yes, definitely. So we are able to do more feedback control on nano DMA. We are specifically allowing feedback control for the static displacement in nano DMA. You have seen that we are able to tune the displacement and amplitude now by a pre-indent on the sample automatically and then use that throughout the testing. So there have been significant changes, including the nano DMA being which means that we have a map of basically CMX tests.
Okay, thank you very much. I think just before we close up, I'd just like to ask one quick question to you, Florian.
Hmm?
When you were doing your nanomechanical characterization of tribofilms, generating both the hardness and elastic modulus, have you looked at H over E ratios, H cubed over E squared, or sort of standard kind of thin film tribological ratios to compare wear resistance? It's just something that struck me while listening to your talk.
Yeah. For one project dealing about molybdenum-based coatings or molybdenum trioxide, there my colleague Norman Mohnfeld from the Forging Institute, he did some nanowear testing to make an wear function on the surface and also make a nano R-shard-based wear model.
Okay.
But for the tribofilm itself, not yet, but that would be also very interesting to apply it there too.
Very good, thank you. Okay, so with that, unfortunately, I think we've had a very packed webinar today, so we are beyond our stated time of 60 minutes. So with that, I think now is a good time to wrap up. So I'd just like to say thank you all very much to all speakers for their fantastic presentations today. Thank you all to everyone in the audience for listening, asking questions. Thank you very much to Brooker for the support for this webinar. As always, please do visit surfaceventures.org, where you can find out more about some of the things that we do, upcoming events, view past events. We've got our next our mini symposium coming up on the 25th of July, so please do go ahead and register for that. Additionally, you can subscribe to our fortnightly newsletter, Modern Surface. This will be moving to an exclusively LinkedIn access, so it'll be best for you to subscribe to it there. And finally, I'd just like to ask you all to take your time to advertise this to your friends and colleagues if they are interested or working in this area. It would be great to have more people following. So with that, thank you very much, everyone, and have a good day.
Thank you.
Good. Thanks, everyone. Bye.
Thanks, bye.